All right, we're going to do day 3 of nuclear physics, studying specifically nuclear reactions. We're going to review a little bit of what we discussed in the previous video, but also expound on it and go a little bit more in depth. Let's start with the alpha decay, which we know is 2 protons and two neutrons that get ejected from the nucleus of an atom. Now, at the beginning, the first radioactive element is called the parent nucleus, and once it decays and becomes a different element, we call that the daughter nucleus. So a parent and a daughter. When one element changes into another, the process is called spontaneous decay, or sometimes we use the word transmutation. But the spontaneous decay just means it happens semi-randomly. In fact, if you look at any one element that's radioactive, one atom, it is impossible to predict when that one element is going to decay, but it becomes a lot easier to predict huge groups of them. But anyway, that's how we get the name spontaneous, is that it seems to be kind of a random spontaneous decay without any sort of provocation. Now, as a general rule, the sum of the mass numbers A must be the same on both sides of the equation, and the sum of the atomic numbers, which is Z, must be the same on both sides of the equation. So when we look at these nuclear equations, we notice that there's 238 nucleons at the beginning, and then at the end, the arrow represents that there's this decay that has happened. In chemistry, you're used to that, right? That the uranium yields this right here. So when we look at the total nucleons, we have 234 plus 4, which gives us 238, so that is balanced on both sides of the equations. 92 protons here, well, we've got 90 plus 2, so we get 92 protons on that side. Another example that you might see is when radium becomes radon. Again, 226 on the one side, and then we have 222 plus 4 makes 226. And then likewise, the protons on the bottom, these two add up to 88. So we should see the same total number of neutrons and protons on both sides of the nuclear equation. As we discussed before with mass defect, in a stable nucleus, the mass of the nucleus is less than the sum of the parts, right? If we added up all the protons and neutrons together, we would expect the mass to be bigger than it really is. And in unstable nuclei, it ends up being the opposite, where once it decays, the mass is less than before. So the nucleus has more mass than the sum of the parts when it splits apart. Now, when it splits, there's a lot of extra energy that is also carried away in kinetic energy. And of course, because the alpha particle is so much smaller than the daughter nucleus, that carries away most of that kinetic energy. Let's take a look at this sample problem. We have uranium-238 and its mass that is going to decay and become thorium and an alpha particle. So write down the nuclear equation. So step 1, write down the nuclear equation, and then determine the energy that's released. So the nuclear equation is just written out with the elements. So I know that I'm going to start with uranium, and uranium-238, and it has an atomic number of 92. That is going to decay and become thorium-234, and that has an atomic number of 90. Now this is a 4, not a 9. And then plus our alpha particle, which is the helium nucleus, that is a 4, 2. And I can confirm that these are balanced because 92 is on the left, and then 90 plus 2 is on the right. We have 238 on the left, and then 234 plus 4 makes 238 on the right. So this is the balanced equation. Oftentimes you'll also see, okay, plus energy, right, because that energy is also released. So sometimes we'll write it out that way. Normally when we write just the nuclear equation, we don't write it, but for the sake of this problem, because we want to find out how much energy is released, it actually makes sense to write, okay, plus energy. So now we can solve how much energy is released. Well, I know that the mass of the uranium was given here, so we get 238.0508 is going to yield thorium, which is 234 plus 0436, plus the helium, which is 4.0026, and then plus some extra energy. So we pull out our calculator, and we find that the 234.0436 plus 4.0026 gives us 238.0462. So I'm going to subtract that number over from the other side. So we subtract the 238.0508 minus that other value, and we end up with the difference of 0.0046 AMU is equal to that energy. Now, keep in mind that AMU is mass, not energy. So it doesn't make any sense to leave it as the AMU there. We need to do the conversion, which reminds us that 1 AMU is equal to 931.5. So if we multiply that by the 931.5, we end up with our energy is equal to 4.28, I'm going to round up right there, MeVs. And that is the amount of energy that is released. Here's a second problem that's just like the other one. You can try this one on your own, so click pause. And another example for you to try on your own, so click pause, and you can write this one down. All right, let's talk a little bit about beta decay and what we would expect there. When a radioactive nucleus undergoes beta decay, the daughter nucleus has the same number of nucleons as the parent nucleus, but the atomic number is changed by 1. There can be a beta minus decay or a beta plus decay, which we talked about in a previous video. So here's what happens, right? We'll have some radioactive element here, but what happens is the electron for beta minus is ejected. So the proton number increases by 1 here because we're losing a charge there. But notice we still have the same number of nucleons because an electron is not a nucleon. For the beta plus, we get the exact opposite, where now our daughter nucleus is going to be 1 less proton because we have the positron that's emitted and carries away that positive charge. The emission of electrons from a nucleus is surprising because, well, electrons don't exist in the nucleus, right? Remember that electrons are kind of orbiting, so to speak, the nucleus. So the nucleus is only made out of protons and neutrons. So where does that electron come from? Well, there's a lot of advanced physics that goes on, but for the short little simple answer is we'll just say that a neutron will kind of just split itself into pieces and it'll become a proton and an electron at the same time and shoot out the electron. So the neutron kind of becomes that proton by making an electron and shooting it out, getting rid of a negative charge, which makes it a positive charge. So again, if you look at this nuclear equation, we have 1 neutron, which is a nucleon but 0 charge, no protons at all. Over here we've got a proton which is 1 nucleon plus a charge, an electron with a minus charge with a 0. So notice how we have 1 nucleon, and then 1 plus 0 is 1, and then 1 plus a negative 1 is 0, and we get a 0, so it's still balanced and works out. Now positron production happens much the same way, but it has to do with antiparticles, but we're really not going to talk about that. That's way beyond the scope of a high school physics class. But just know that it's the basic idea that a neutron will shoot out the positron, the proton will shoot out the positron to become. All right, let's look at a sample problem of a beta decay. So we have thorium that's going to become protactinium, and we want to write down the nuclear equation and find the energy that is released. So thorium-234 is going to become protactinium-234. And to make all of this balanced, we've got the right number of nucleons already, so I know I'm going to have a 0. And then I've got 90 here, and I've got 91, which means I need a negative 1. So a negative 1 charge means it's going to be an electron. So this is the equation. Again, sometimes we can write plus energy. We don't usually write that when we're just writing down the nuclear equation, but because we're asking for the energy right now, we're going to write it down. Now thorium is a 234.04359. Protactinium has a mass of 234.04330. Now, I know that electron technically has mass, but remember it's like 1/2000th the mass. So rather than writing it down, it's going to have a negligible effect on our calculations here. We're just going to find this mass defect by subtracting these over. So 234.04359 minus 234.04330. 0.4330, and we get 0.00029 AMU. Now again, this is not really the energy, this is the mass defect. So to convert that, we multiply by the 931.5, and we end up with 0.27. We'll just round up to that. MEVs. Ta-da! Okay, here's another couple of sample problems that I'll let you just try on your own, so click pause. And again, just click pause on this one, and you can spend a moment solving this problem. All right, let's talk about gamma decay. This one's a bit different than alpha and beta. If you remember from chemistry how electrons only existed in specific energy levels, it just so happens that a nucleus is like that there are specific energy levels of a nucleus. Now, very often a nucleus that undergoes a radioactive decay still has some extra energy that's left over inside of it. So it might shoot out that positron or electron or the alpha particle for that alpha or beta decay, but there's still like this extra energy that's kind of pent up inside. So when that nucleus changes from an excited state, meaning that extra energy, into a lower state, we use a little asterisk to denote it. And that high energy photon shoots out, and that's the gamma ray. So when we undergo gamma decay, the nuclear notation would look like this, that we have some sort of element with an asterisk showing that it's an energetic, that it has extra energy inside of it. Once it decays, notice that the A and the Z doesn't change because no nucleon has been ejected, no charge has been ejected. It's just the extra energy. So the excited state becomes unexcited and just becomes a regular radioactive or stable element. Now, gamma decay does not cause a transmutation of one element into another, and there really isn't a convenient way to predict gamma decay. But another way that gamma decay could occur is because of the beta decay. So frequently what will happen, here's an example of boron, but boron will decay into the carbon, but this carbon is going to be excited, which is represented by that asterisk right there. This represents a neutrino, which we're not going to study this year. You don't need to worry about that. But we can see that, okay, this has undergone a beta minus or beta negative decay. Well, because this is excited, it doesn't like to stay excited, so we can actually write out a second equation that shows how this excited carbon-12 becomes an unexcited carbon-12 by releasing that gamma ray. Let's move on to something called decay chains. Previously, we talked about this band of stability, right? So right here, this black line that I'm now drawing with red, this represents all of these stable elements that are not likely to undergo any sort of radioactive decay. And then we talked about how above it we're likely to have our beta negative, below it we're likely to have a beta positive, and way up here that's really big is likely to be an alpha decay. But really this is just a general trend that we would expect. It's the most common way for it to decay. But it turns out that a single element can actually decay in many different ways. I didn't realize that writing would show up on the next picture too, sorry. So let's take a look at what could happen. So protactinium, right up here, is going to undergo alpha decay to become actinium. Now actinium can actually do one of two things, or at least actinium-227 can do one of two things. It might undergo a beta minus to become thorium-227, or it might undergo an alpha to become francium-223. Notice how all of the numbers work out. With a beta negative, we increase by 1 proton, but we keep the same number of nucleons. For francium, we decrease the proton number by 2 and decrease this right here by 4, right? So there's two different possible paths. Well, now at this point, if it became the thorium, then it has to become a radium, and then it'll become radon, and then so forth. Well, francium could become radium, or the francium could become the astatine, right? So there's this whole chain of events of what could happen, even though the band of stability tells us what is most likely to happen. The important thing to note with these chains is following the type of decay. So if these were, like, for example, in the homework, if this is blank and you have no idea what this is, and it says, okay, actinium is going to undergo alpha decay, what is this going to be? That's when you have to use your nuclear equations and say, okay, I need to subtract 2, so this is going to be an 87, and then you have to look at the periodic table and say, okay, what element is 87? Oh, that's francium. Okay, so that's Fr. It's going to lose 4 nucleons, so you subtract 4 at the top, yada, 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 right? So you should be able, if I give you a starting point right here, you should be able to fill in the blanks of a bunch of empty things just by following the decay type and either increasing the proton numbers or decreasing the proton numbers based on the alpha or beta decay that is happening. So what are some of the practical uses of radioactivity, right? How can we use this to our advantage? One of the big things that we like to use is something called carbon dating. And no, this isn't a dating website for carbon-based life forms. This is how we age things that have died a long, long time ago, right? Now, it just so happens that carbon has a couple of really common isotopes, carbon-12 and carbon-14, that are both relatively common in the atmosphere. And the ratio of how much carbon-14 there is in the atmosphere is pretty constant throughout the years. There is a little bit of fluctuation, which we'll talk about in a second, but for the most part, it's pretty constant. Anything that is alive and is respirating, that is taking in the air, is going to absorb naturally some of that carbon-14 that's in the atmosphere. Once it dies, it's no longer exchanging with the atmosphere, and so the ratio starts to decrease, right? So all living organisms have the same ratio as the atmosphere because we're constantly interacting with it. But when we die, we don't absorb the carbon-14. Now, carbon-14 is radioactive, and it has a pretty predictable half-life. And so all we have to do is take a look at something that has died and look at the ratio of carbon-12 to carbon-14 and see how much discrepancy there is based on what we would expect there to be. And then we can predict how old or how long ago that object had died. All right, so here is the nuclear equation. If we know how long it takes, which for carbon-14 is 5,730 years, so we can just kind of work backwards and age that thing based on that ratio of what is there. Now, like I said before, there are some fluctuations in the carbon-14 in the atmosphere. So there is some uncertainty. We typically say the uncertainty is about 15%. But still, even then, carbon dating is very, very accurate for things that are on the order of tens of thousands of years old. Once you get significantly older than tens of thousands of years old, there's not enough carbon-14 to really measure a huge difference. And so it becomes less reliable. Now, radioactive nuclei are generally classified into 2 different groups. So we have unstable nuclei that are found in nature, which is what we call that natural radioactivity, right? Things that will naturally decay. And then there's nuclei that are produced in a laboratory where we artificially create these nuclear reactions, and those will exhibit artificial radioactivity. Natural radioactivity constantly supplies our environment with radioactive elements that would have otherwise disappeared long, long ago. It is possible to change the structure of nuclei by bombarding them with energetic particles. So such changes are called a nuclear reaction. So what does that mean? So if we go back to like Rutherford's experiments that he did, right, he found that protons were released when alpha particles were allowed to collide with nitrogen atoms. So we can undergo an artificial decay by taking an alpha particle and bombarding it with the nitrogen. Now notice if we look at our equation here for the nuclear equation, I've got 2 helium and 7 nitrogen, and he said, okay, well, 1 proton is ejected. So 7 plus 2 is 9. So that means I need to have an 8 right here, which is oxygen. And then again, if we count up the number of nucleons on both sides, we'll find that both sides add up to 18. So this is this exact same process that we used for that natural radioactivity, but the difference is with artificial is that we generally have 2 different objects here on this side, right? In this case, we're doing alpha plus some nitrogen is going to yield some sort of radioactive process. So it begins with two stable isotopes, which is helium and nitrogen, but it produces two different stable isotopes, hydrogen and oxygen. Okay, let's take a look at this. A particle strikes, or an alpha particle strikes aluminum 227. As a result, an unknown nucleus and a neutron are produced. So identify that nucleus that is produced, including its atomic number and everything about it, right? So alpha particle, that's a helium, that's 4 and 2. We're going to collide with aluminum 27. This is going to create some unknown plus 1 neutron. Okay, well, let's take a look at our tops. So 4 plus 27 gives me 31 on this side. So I need to have 31 on this side. I've got 1 right here, so that means I'm going to have a 30. 13 plus 2 gives me 15. And if we look at the periodic table for 15, that is a phosphorus element. So this is what we would expect here, and it's a phosphorus 30 because that's the total number of nucleons that are right there. Why don't you go ahead and try this one on your own and look at this unknown element. Pause. Okay, here's another one. Another way to look at this one is basically saying which is the possible reactions. Just count up the total number of nucleons on the top and make sure that they're balanced, right? If it's not balanced, then it's not possible. Count up all of the protons down at the bottom. And again, if it's not balanced, it's not possible. Right? So go ahead and click pause and determine if each of these is possible. Okay, and our last one, identify this unknown particle. And that is it. Have a wonderful day.